Welcome to Review Lecture number 17, second part of our two-part series on linear regression. And this is the last lecture. 17 lectures plus an intro for a total of 18 videos for my online review course of undergraduate probability and statistics. If you've made it this far, you've gone through about 3 weeks of a typical university course, and it would normally be the first 3 weeks of a graduate level class that I teach on data analysis and other statistical techniques that graduate students will need. So I usually spend the first 3 weeks of that semester reviewing undergraduate probability and statistics, and so I've taken that 3 weeks and put it into these 17 lectures plus the intro. As I've said at the very beginning, it doesn't cover all aspects of undergraduate probability and statistics. I have pulled out what I consider the major pieces and left behind some still important things that I just don't have time to review. Also, it's not, as I've said before, a class in probability and statistics in the sense that you could come in fresh without knowing anything and take this course and come away very comfortable with your knowledge. I'm assuming that you've already had a class in probability and statistics, and then I'm just reviewing the basics to refresh your memory. So I'm assuming you've already learned about linear regression. In fact, probably have used linear regression multiple times in various applications as well as in an undergraduate statistics class. So we're going to finish up this review class by looking more closely at the aspect of linear regression and using some of the math preliminaries that we set up in the previous lecture. In the previous lecture, we talked about least squared error regression and maximum likelihood estimators in linear regression. Our model: the expectation of y given x equals ax plus b. X is a random variable, y is the random variable of the output, and the expectation of y given x means if you tell me what x is, y will have some distribution, and the mean of that distribution will be linearly related to that x value, ax plus b. That's what our model says, and it's the standard linear regression, the standard way of thinking about how y relates to x in a linear fashion. Then we found that a and b must satisfy these equations. B is the expectation of y minus the slope a times the expectation of x, and our slope a is the covariance of x and y divided by the variance of x. Then we created various estimators for a and b by looking at our estimators for covariance, variance, and expectation. The result, well, b was very simply y bar minus a x bar, where y bar and x bar are the sample means, the mean of all the y data points, the mean of all the x data points. And a came from our estimators of covariance and variance, and we noticed that 1 over n or 1 over n minus 1 cancels out, so it doesn't really matter whether we're using a sample estimate for covariance and variance or a population estimate for covariance and variance, because those terms drop out. These are the results we got by making a least square error estimate, but they're also the exact same estimates we get using a maximum likelihood estimator, as long as the y's and the x's are normally distributed and identically distributed. So IID variables. Now, with that in mind, let's review all of the assumptions that went into an MLE linear regression estimate. First, we assume that y is linearly related to x. As we saw in the lecture on correlation, if y is related to x in say, a quadratic fashion, then our linear regression won't really have much meaning. We'll assume that the xi is known with certainty for every I. That is, only the y data point, yi, has uncertainty, some of which is explained by x, but some of which is left over. That is, some uncertainty in y that comes about from some other source than our linear model. We'll assume that all of the yi are IID normally distributed and that there are no outliers. We've talked a little bit about robustness and the robustness of estimators, and our estimators, MLE or LSE, for the slope and the intercept are not robust. In other words, even one bad data point will completely screw up our analysis and give us screwy results. So, given that background, what those assumptions are, let's look a little bit more closely at a set of best practices of how to actually accomplish a linear regression. Now, it can be easy to skip some of these steps, especially since linear regression can be performed so readily using software today. In particular, packages like Excel, that with just clicking a button, you can create a linear regression. But we need to be careful because we can use these tools to get wrong answers just as easily as we can use them to get right answers. What are our steps in linear regression? The first, maybe even the most important, is to create a plot of the data. Plot y versus x in a scatter plot and look clearly and carefully, is the assumption of a linear relationship justified just by looking at the data? Sometimes you can see right away that there is a nonlinear behavior going on, so fitting a linear function to a nonlinear behavior may not be reasonable. Also, are there any obvious outliers? Because again, our regression is not robust and one bad data point will screw things up. I'm not going to go through in this class much detail on how to define carefully or rigorously what an outlier is, but keep in mind that you may have to if you see some data points that look like they don't belong in this relationship. Then, what do you know about the underlying probability density functions or random variables x and y? Do you have a reason to assume that they're normal distributions? Or are you just making that up? Our MLE estimator assumed they are, so I'm just going to assume they are. Well, if you don't have any reason to assume they're normal distributions, they might not be. They might be something completely different, thus rendering these estimates bogus, not very good estimates. If I have an underlying distribution of my data which is far from normal, then the estimators I get from assuming normal distribution, that is our least squares error estimates, may not be very good ones. Then, once this background is accomplished, background steps, we perform the regression. This is the easy part. This is pushing a button on a piece of software. The next step is to plot the residuals. This allows us to check the assumption of IID normal. And I'll show you what I mean by that in a moment. So, let's go through this example by first creating an XY scatter plot of the data. Now, I just made up some data. I plot the y variable versus the x variable. I show the data points, and I create a best fit line. The first thing I do is look and say, that looks reasonably linear. In other words, there's no obvious nonlinear behavior jumping out at me when I plot the data. My model will be the standard one, yi equals axi plus b plus a residual. I put it in this form to emphasize the residual. Additionally, I'll define the predicted value at y hat I as simply being axi plus b without the residual piece. So the predicted value is the value I would get given my best fit values of a and b. The residual then is simply defined as the actual data point minus the predicted value of the data point. And you can see by plotting the residual that it's the distance, the vertical distance along the y-axis between the data point and the best fit line. And you have one of these residuals for every data point in your fit. Well, what am I going to use these residuals for? When I'm done doing the fit, I will take a look at these residuals and check how do they behave. And I'll create a second scatter plot, an XY scatter plot of the residuals. I plot the residual versus either the X variable or Y hat I. Now it seems more convenient to plot it versus the X values, the XI. But sometimes we have multiple regression. That is, we have some output Y as a function of more than one input, X1, X2, X3, or A, B, C. Well, you can come up with different names for the multiple variables you might use as your inputs. Then plotting the residuals versus the predicted value gives you a simple two-dimensional graph, even though you have a multi-dimensional space, which is why we like to do that. You can also plot a histogram of the residuals. This is especially valuable if you have lots of data. If you have 10 or 20 data points, histograms are kind of hard to use and interpret. But if you had 100 data points or 1,000 data points, then histograms of the residuals can be useful in checking the normal assumption. There are other more sophisticated tools to find out whether you believe the distribution is normal. We're not going to be able to talk about those in this class. But what I'd like to do here is simply inspect the graph visually. Now we know that the mean value, my little bar over the E didn't quite show up on the screen here as perfectly as we would like, but the mean value of all the residuals is 0, and we see that here. If I draw a line across at 0, about half above, half below. But what we're going to look for is violations of the IID normal assumption. Do you see trends in the residuals? If I see a trend that looks linear, that means I didn't get a very good job. I must have made some mistake in my best fit. If I see a trend that looks higher order, quadratic or something, then that probably means my data has some trend in it that isn't being captured by a simple linear model. I might also find that the spread of data at, say, low X values is smaller than the spread of data at high X values. That is, I can see that the variance of the residuals is varying as a function of X. If that's the case, they're not identically distributed. And we can see a violation in this assumption. That's one of the more common violations, by the way, that the residual spread is different in one range of X than in another range of X. There are more rigorous tests to establish whether we think the IID normal assumption is valid. Here we're not going to employ those rigorous tests. We're simply going to look at visually the information and in this residual plot and see what we think. And this is, by the way, a very powerful tool because our eyes are pretty good at spotting trends. Now, another important parameter that comes out of our fitting is something called the goodness of fit. The goodness of fit metric goes by the name of R squared. It's usually a capital R, but R squared is nothing more than little r squared, which is the correlation coefficient, or more particular, the Pearson correlation coefficient, the product moment correlation coefficient, little r, that we talked about a couple of lectures ago. So if we take that correlation coefficient, linear correlation coefficient value r, and we square it, we get capital R squared. And I'm not really sure why we use the capital R, but we always use the capital R after we square it. Well, little r, the linear correlation coefficient we saw before, was the covariance of x and y divided by the square root of the variance of x times the variance of y. And r squared then, which is simply the square, is the covariance squared normalized by dividing by the variance of x and the variance of y. But with just a little bit of manipulation, we can prove that r squared is also equal to 1 minus the variance of the residuals divided by the variance of y. Now, how can we interpret r squared given this equation? Well, the variance of y is simply how much is y changing in this particular set of data. The variance of the residuals is how much of the variance of y didn't get captured by our linear model. Remember, the residual is the variation that's not explained as being linearly affected by x. So, r squared is quite simply the fraction of the variance of y that is explained by the linear fit. Right? This is the fraction that's not explained by the linear fit. 1 minus that, the fraction that is explained by the linear fit. If r squared is 1, that means all of the variation in y is completely explained by the linear model. If r squared is 0, that means none of the variance in y is explained by the linear model. And the residuals are just as big as the variations in the residuals are just as big as the variation in y. So those are the two extremes. R squared goes from 0 to 1, and the way we interpret it is what fraction of the variance of y is explained by the linear fit, that is explained by x. Now, when we think about any statistic, we should always be thinking about how we can describe the uncertainty of that statistic. And that's because we do everything based on samples, not based on the entire population. Our population model says yi equals, now I'll say alpha and beta, but a and b, linear related to the xi, plus a residual, where we're going to model our residuals as being normally distributed with a mean of 0 and a variance of sigma sub epsilon squared. When we create our model and use it, we'll have a number of statistics that come out. First of all, we'll have the slope, a and b. But also, we'll have predicted values, yi. It might be very useful to say, what is the predicted value for this particular x value? Another statistic that comes out of our linear regression is r, the correlation coefficient. Whenever we report a statistic, we should always report confidence intervals around that statistic. It's the uncertainty levels. So we can say, based on this sample, we are 95% confident that the true value of the slope falls within this range, just like we did with mean and any other statistic. Confidence intervals are required for any statistic that we get from a sample. How do you do that? Well, we have to know the sampling distribution. Well, the sampling distribution for A, the slope, B, the intercept, and our predicted values, y hat, I, are all unbiased and t-distributed. R, on the other hand, is a little bit more complicated. It has a more complicated sampling distribution. We're not going to worry about that, but we are going to worry about A, B, and y hat. The degrees of freedom are n minus 2 because the linear fit extracts 2 values out and eliminates 2 degrees of freedom because of that. The variance of A will equal the variance of our residuals divided by n times the variance of x. So I've got a set of data. I can estimate the variance of the residuals. I know the variance. I can estimate the variance of x using the variance of my x values in my data, and n is of course the sample size. The variance of B is also the variance of the residuals divided by n, but now it's a function of the mean value of x squared divided by the variance of x. Of course, we can estimate all of these parameters and use them in a confidence interval calculation. Let me, before we talk more about that, describe the meaning, just intuitively, of these equations. We want to predict A with small variance, right? We want to have a good value for our slope. We don't want a lot of uncertainty in the extracted best fit slope. We want small variance of A. How do I get small variance of A? Well, of course, if the fit is really, really good, if the variance of my residuals is small, that reduces the uncertainty in the slope A. Right? If all my data falls on a line exactly, and the variance of the residuals is 0, well then I don't have any uncertainty as to what the slope is. But given a certain amount of variance in the residuals, to get a smaller variance in A, what do I need? I need a larger sample size, bigger N, and a larger variance in X. What does a larger variance in X mean? I'm defining an experiment where I vary X and I measure Y at all the different values of X. What this means is I want the range of X to be as big as possible. I'm working my way through a number of X values. At every X value, I calculated a Y value and I get a fit, a straight line fit in that data. Well, the wider the range of X, the less uncertainty there is in the slope. If all of my X values are crowded around a very narrow range, then I have much more uncertainty in the slope. So this is how it tells you something about how to design your experiment to minimize the variance in the slope. The variance in B, well, it has the same dependence on the variance of the residuals and the sample size, but now it has this extra term, which is how does the variance in X compare to the mean value of X? Again, I want a wide range, but now I want that range to be wide relative to the mean value, and that's what reduces the uncertainty in the intercept. So, we have one more important statistic that we want to understand, and that's the uncertainty in the predicted values. Often, the whole reason that we create a model is so that we can make predictions using that model. So if I create a linear model, I want to be able to use that linear model to predict the outcome of some future experiment. Well, what's the uncertainty in y hat, the predicted value? Well, it comes from different things. It comes from the uncertainty, that is the spread about the mean in a y that is normal, that is usual, I mean to say. And that comes from the residuals. How wide are the spread of residuals? But also, I get uncertainty in my predicted values that come from uncertainty in A and B, the best fit slope and intercept for my linear regression. Any uncertainty in A and B will result in uncertainties in the predicted values of y. Again, the sampling distribution will be students t and have a degree of freedom of n minus 2. If I have a large n, then the students t distribution will revert to a normal distribution, and that will be the large sample limit. The variance in my predicted value y hat will have the same term, the variance of the residuals divided by n. But now I will have to look at how different the xi value is that relates to my predicted value of y compared to the mean. If xi is right in the middle of the range, that is right at x bar, then I get no added uncertainty that comes from A and B. But the further away from the middle of the x range that I'm trying to make a prediction of y, the further away xi is from x bar, the larger this added term becomes. Extrapolating gives me larger uncertainty. I mean, just think about it. If I have a slope, and then I think about some small wobble, the slope has uncertainty. Well, the further away I get, the bigger the uncertainty in the predicted value will be caused by small uncertainties in the slope. Extrapolating gives me larger errors than if I stick to the middle of the range. Well, we should really be very careful about extrapolating anyways, simply because our linear assumption may fall apart outside of the range of our data. But at the outside of the range of data, I have the maximum uncertainty in my predictions. As always, once we've got our sampling distribution and an estimate for the variance, we can use that to construct confidence intervals. And every time we report a best fit slope and a best fit intercept, or a predicted value from our model, we should always supply the confidence intervals that go around it. Unfortunately, many scientists and engineers, and certainly many students, fail to perform this very simple calculation, which is, in my mind, required for any best fit. All right, let's review lecture number 17. What have we learned? As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material again. What are the assumptions for a standard least squares linear regression? Why is it a good idea to plot our residuals after we've done our fit? What is the goodness of fit, R squared, and how do we interpret its value? And finally, you should know how to construct confidence intervals for the linear fit parameters A and B, the slope and the intercept, and for predicted values that come from our fit equation. If you can't do that, you haven't really performed a linear regression. That's the end of our last lecture and the end of our review course on undergraduate statistics. I hope that you will have found this review course valuable, and that after going through it, maybe even working some of the homework problems that are on the website, and possibly even taking the practice final exam that's on the website for this review class, you will feel comfortable that you're ready to move on in your quest for more knowledge about probability and statistics. Thank you for sticking it out to the end. Good luck in your statistics career.